All right, my friends, we are going to take a look at what's called a combination circuit, a circuit that has resistors that are wired in such a way that they have both series and parallel aspects. And so what we're going to try to do here is find the current that's flowing through each of the resistors in this circuit right here. The way I like to kick these off is by labeling voltage where I know it. So here the voltage would be 10 volts because we haven't gotten to any of the resistors yet in the circuit. We're right near the positive terminal of the battery. And likewise, the voltage here will be 10 volts. We have a voltage of 0 volts at the end of the circuit here after the last resistor. And so to kick this off, we'll go to use Ohm's law, V equals IR, to try to find the current at different places in the circuit. Now, right away, we would run into a roadblock if we tried to use Ohm's law on any of the resistors individually. And the key is that we don't know the voltage at this location here where I'm blinking the letters on and off here. And the idea is if you tried to say use Ohm's law on this 6 ohm resistor individually, you don't know the voltage drop to plug in here. It drops from 10 to some value we don't know. And likewise, that's the case across the 1 ohm resistor as well. And we also can't plug in the voltage drop across the 3 ohm resistor because we don't know the voltage at this location in the circuit. So this is really the key here, why we are not able to use Ohm's law on any of the individual resistors quite yet. And so what that means is what we're going to have to do is use Ohm's law across the entire circuit or applied to the whole circuit. And so what that means is we are going to have to find the total resistance of the circuit. Well, the 6 ohm resistor and the 1 ohm resistor together happen to be wired in parallel. So 1 over the resistance, the composite resistance of those two, will be 1 over the first resistor plus 1 over the second. The reason I know those two green resistors are in parallel is they have the same voltage drop. It's going to go from 10 to some mystery number and 10 to some mystery number. So these two branches are in parallel, even though they don't look geometrically parallel. Well, let's go with this. So 1 over the resistance that those two are going to make together is going to be 1 over 6 plus 1 over 1. Or so 1 6 plus 6 6 would give you 7 sixths. And then we have to take the reciprocal of that to get 6 sevenths for what I call R parallel. So together, these two green resistors act like one 0.86 ohm resistor. Well, so the grand total resistance for the circuit is 3.86 because you would have the 0.86 that comes from these two green ones plus the 3 ohm resistor that is in series after that parallel combination. So our grand total resistance is 3.86 ohms. Well, so now what we can do is use Ohm's law, delta V is IR, on the entire circuit. So we have a 10 volt battery. There is a 10 volt drop across the entire resistor network. That's going to be equal to what I call the total current times 3.86 ohms. And solving for the total current there gives us 2.59 amps. And what that means is that we have 2.59 amps leaving the battery and then also returning to the battery, and that is going to be then the current in our 3 ohm resistor. And so all we have left is to find how much current is in our 6 ohm resistor and our 1 ohm resistor. There are a number of ways to do that. One way is to first apply Ohm's law now directly to the 3 ohm resistor. And so we can say, well, what's the voltage drop across the 3 ohm resistor? Well, we know the current in the 3 ohm resistor is 2.59 amps, and the resistance of the 3 ohm resistor is, of course, 3. And so our voltage drop across this 3 ohm resistor is 7.77 volts. Well, that's a big deal because we now know the voltage over here must be 7.77 since that's the drop across the 3 ohm resistor. But maybe more importantly is we now have learned what these mystery voltages, where these question marks are, the voltage there must then also be 7.77, right? These areas are all connected here by the same conductor with no resistances in between. So the voltage here is now, we now know it to be 7.77. Well, now we can simply use Ohm's law across individual resistors since we do now know the voltage drop across them. So let's just pick the 1 ohm resistor. Well, on this 1 ohm resistor, we have a voltage drop of 2.23. Now, why is that? It starts at 10 and it goes down to 7.77. So that's a drop of 2.23. And then that's going to be equal to I times the resistance of 1. So what we learn is that 2.23 amps then go through that 1 ohm resistor. So there it is. And then finally, to get the current in the 6 ohm resistor, we can just take the grand total of 2.59 and subtract off the 2.23 that went cruising through this middle branch. And what that will do is give us 0.36 amps, which cruises through the 6 ohm resistor. And what you'll notice is within some rounding error, this 0.36 amps, that is 1/6 of the amount of current that flows through the 1 ohm resistor, and that is because it is 6 times easier to go through the 1 ohm resistor than through the 6 ohm resistor. So hopefully you find that helpful, and thanks for watching.